Okay, we're going to look at hydrology and ratings, or hydraulics, and things around rating curves and controls, offsets, breakpoints for rating curves. So let's just start with a general hydrology. So hydraulic control controls the depth of water at the recorder site. So there's always there are three types of controls, not always three at every site, but there are three main types, and that's the first one on the left, which is a section control. And the section control is this lower bed, which you see here, which is very obvious, a break in the surface of the water. Ideally like this, it's bedrock, so it's not going to change. But this is an ideal example of a section control or bed control of a stream or river. And then we switch to a channel control here, which has it's just a continuous run, so there's no obvious break like we see here. So no section control. The only control of the river here is the channel, the sides of the channel, which would be a combination of the geometry, the friction, and the slope. And then we have, in flood conditions, overbank control. So it's going over these banks, and the control is various controls, usually vegetation and higher channels. So three types of controls. So just to highlight the section control a little bit more, when a single cross section in a stream acts as a control, we say the recorder is under section control. So here's the recorder here on the left, or the true right of the stream. You can see the section control. Here's the recorder pool. So the height of water in the pool is directly related to the geometry of the section control. So this section control here and the size of it, the height of it, and the depth behind. So the noticeable break in the water surface occurs at the section control, and it's easily identified. Here's a more common one you'll see in a stream, which is, again, this is a section control through here, defined by the break from a run to a riffle. So across here, there's something caught on the control there. But this could be made up of sand, gravel, or cobbles and boulders, which is possibly in this case here. So here's the section control. And we can have artificial section controls. So we can have sharp crested weirs, like this 120-degree weir here. We've got flumes, and then broad crested weirs here. So three types of artificial. Here you see the other slight problem you can have at sites like this. If you have your stilling well too close to your weir, this one here even is probably okay because it's a fair way from the V-notch, but if it's too close, the drawdown effect can also give a false offset, if you like. So ideally, a site like this where you've got your stilling well with intakes in this pool, and it's quite a long way down to where the actual weir is, so there's no drawdown effect on the actual stage being recorded, something to note. But something to keep in mind is the sensitivity of the rating shape. And what we're after is a sensitive relationship between the stage and the discharge, not insensitive. Because when it's insensitive, it means that with a small change in stage, here, there's a large change in flow. So you might only have a few millimeters change in stage, but you might have tens, maybe 100 cumecs in a big river change in flow. So that's not sensitive. So sensitive controls are the best. So let's have a look at a few coming up. So here's an example of a sensitive and a stable control, in which you have volcanic bedrock here. It's not going to change. It's like a natural V almost. So it's very sensitive, ideal really for a gauging or recorder to be where we're standing. Another example here, even though it's a complicated control, the section control here is very stable, being bedrock, and it's almost going to go into a V in places as it gets lower, so it does have the sensitivity. And of course, a bad example here, stability is very bad here. You've got loose gravel, debris being caught on whatever this is in the water here, banks of vegetation are crumbling, so not a good location. Again here, fine silts and gravels, collapsing banks and vegetation, so very unstable site, would create a lot of rating work. Like every time there's a flood or fresh through here, it's going to wash things, change things around, and you're going to have to start again with more gaugings, brand new rating. So the ideal characteristics of a section control for ratings. So the materials of the section control are stable, and it limits adjustment of the rating. This site, as we saw before, it's very stable with bedrock and large boulders. So it's going to take a big flood to change that. So most flows will go through here without changing this. Therefore, we won't have adjustments. We won't be doing adjustments or creating new ratings. The section control creates a relatively deep pool where the recorder is. So you can see the recorder's over here. It's in a deep pool. It's never going to go dry if things do change. It's always going to be in water or underwater. The section control creates relatively slow velocities in the recorder pool. So this is slowing down velocities here. So it's easy to record. You're going to get a nice trace. Where if you're trying to record here in this riffle, it's going to be very noisy trace. The record just won't be smooth at all where it is here. The flow contracts as it approaches the section control. This enhances the sensitivity of the control. So you can see here that the wider river is contracting to a smaller area. So again, that adds to the flow coming down, reacting with the stage, far more sensitive. And section controls are perpendicular to the flow. So ideally, we want them directly across the river like this. And the streamwise length of the section control is short and easily identified point of zero flow. So this being short too helps as part of the contracting of the flow. And then we can easily identify the deepest part and where the point of zero flow, this is where the water will stop flowing down here and it'll just be a pond, a still pond. So this is important for our rating construction, as you'll see. So here's an example of, again, a larger river, but with a section control, very obvious with the break here, and then it'll change to a channel control as it rises up the banks here. And this is an example, again, is a slightly smaller river, but slightly more complicated because you've got a control here that's not perpendicular. So if it was perpendicular, it'd be running across here. This one is running down the length of it almost and diagonally across. So we've got low points here. We've got another low point here with a channel. But in saying that, it's still quite stable because they are big boulders or cobbles in here. So it doesn't change that often. And you can find the point of zero flow, which is possibly here for this river because our recorder's where we're standing. You might want to notice the banks too when it goes from section control to channel control. They're not that stable. It looks like they have been moving, crumbling, and they could be eroded. So possibly not the best, but it's stable down further, of course. So the point of zero flow is also known as the offset. So this diagram here just explains it, and it's rather busy. But if we start by envisaging this meter rule here as the staff gauge in our river, and what we need to know this this value is a crucial value here, basically, because this is what we're recording. The measured gauge height is the height of the river there as it goes over our control. This is our section control here. And the height of water here is what we're measuring back against the staff gauge and with the recorder. So this height here down to when it stops, or the point of zero flow, is crucial for our rating development, as you'll see. So this measured height down to this depth here is called the hydraulic head, and that's what we can scale off the side here. So looking at it, the hydraulic head is made up of the gauge height, so that's the reading we're reading on the staff gauge at the time you're standing there, the time you're measuring this depth. We need to know that height, and we need to subtract this gauge of zero flow, or point of zero flow, which is our offset. So when we subtract that, we get this value here. So we need to know this offset value so it's not included in the deriving of discharge in Aquarius. So you'll see how that works when we get to the rating curve later. So this is important at our sites if we can establish this point of zero flow. And you can do that at any stage by walking down, if you can weight it, or using the boat with an ADCP maybe. You might normally gauge it here, but you could drift down and do a cross section just to see where the lowest point is and where the river will stop. So we're at point of zero flow. So the practical application of subtracting the offset from the gauge height is that the measurements of hydraulic head, these measurements of hydraulic head versus flow, will plot in a straight line on log paper. And that's how we're going to create our rating after. We're using the log straight line method. So we need these two values for that. So here's another ideal example with a V-notch weir trying to find the point of zero flow or the offset. In this case here, the bottom of the V is at 1 meter. I mean, if it was at zero, it would be nice because then whatever the water surface is, that is your offset. But in this case here, it's at 1 meter. Our water surface is measuring at 3.5 meters. So therefore, we need to subtract those two. So the point of zero flow equals the recorded depth minus the water depth. So in this case, the recorded depth is 3.5. We're subtracting the water depth, 2.5, which is the head or depth, and that gives us a 1 meter point of zero flow or offset. And how to measure that point of zero flow? It should be measured whenever possible. So if you can possibly do it through different methods, here's an example here of you wading down to the section control below the site, finding the deepest part, using your wading rods and measuring that depth of where the water, where you can envisage this. If the water level keeps going down, it's going to stop flowing at this point here. So we need to know that depth there. So how to determine the offset? So for a rating curve segment for a section control, the point of zero flow is a good first approximation of the scale offset. Now these are the offsets we use down here in the offset manager, you'll see. So this is a really good indication of our point of zero flow is going to be close to whatever we measure of this point of zero flow. And then we can do some fine adjustments after that. But if the rating curve segment is for a channel control or overbank flow, the offset is best determined by trial and error. This is because we can't usually go and measure this. You can have a try, you might be obvious, but if you can't measure the point of zero flow, you really have to use trial and error when we get to the rating toolbox and using the offset manager. Just a word of warning, don't use this get best scale offset. It doesn't seem to work very well and it just makes things worse at times. So yeah, just a warning there, we don't use that. So in the case of multiple offsets, the point of zero flow for the V-notch weir, as you can see here, is around 2.9 meters. However, using 2.9 as an offset for the flow over the wider rectangular weir, see the rectangular one here, won't produce a straight line. So the point of zero flow of the rectangular weir would be the gauge height at the crest of the weir, so at this point here, this gauge height here, which is about 4.3. So the amount of flow running over the rectangular crest will be much, much larger than the flow just through the V-notch. As such, we say the effective point of zero flow, or the second offset, is the point of zero flow of the rectangular weir. So there's our first offset, the bottom of the V-notch. Second offset, the flat, broader crested rectangular weir. So you've got two offsets for this rating, but in reality it may be slightly lower. That's the second offset, depending on the flow volume going through here. So it could actually reduce that offset due to this, taking into account the flow at this point here. So that's why we have two offsets in places, and maybe a third when you're going to overbank, overflow, flood. You're going to have another offset here, which again could be hard to establish. It could be a bit of trial and error to find that one. And here's another example here in a semi-natural environment where it's man-made weir. But here you can see we've got our three offsets, our low flow through this small V-notch at the end, our medium flow, so our next offset is at this height, with a low flow will be a lower offset here, and then when it goes over the banks, the high flow. So we've got three offsets, two break points, first break point, second break point. So back to this section again, hydraulic controls. So when a single cross section of stream acts as a control, we say the gauge pull is under section control. So at the moment this site here is measuring under section control. So the height of water in the gauge pull is directly related to the geometry of the section control. So this height of the water here in the gauge pull, the recorder pull, is directly related to the geometry or shape of this control. There's a break in the water surface at the section control. The control is easily identified, and the point of zero flow again in here, probably this deepest part, is easily found. So in this case here with higher flows, the section controls can be drowned out. So there may be a section control in here somewhere, but it's drowned out. There's no noticeable break in the water surface. So now we're under a channel control. And again here, when physical characteristics of the stream reach controls the height of the water in the gauge, we say the gauge is under channel control. Okay, there's no longer a gauge pull, it's just a long run of the river. So the height of water, and if we had a recorder here where we're standing, the height of water is related to the geometry, the shape of the section, the slope of the water down here, and the roughness of the bed, the roughness of the channel. That's all controlling the height of the river. So that is a channel control. And then extreme high flows, the capacity is exceeded and the flow goes over bank. So let's have a look at this in a diagrammatic form. So channel control at this stage, this is just a channel control. It's a single section. Even though there's a section control here, the range of stage is always up in the channel. So that we say this river would be in channel control. It never gets down low enough to be affected by the section control. And this is how it would look. Our rating curve would just be a nice straight line, one slope in the log in Aquarius, which we'll see later. And this is a typical site here. This is a site that has a channel control only, no section control effect. So it's just one straight line. The gauges are plotting nicely on it. This is a large river too. You see it's 1,000 cumex here. And that's it in arithmetic or linear. And that's how the site looks there. So it's a large river, no section control, just a channel control all the way down. Maybe some bank control here as well as it bends. So the channels here controlling the height at the gauge. So if we have a section and channel control, so two segments, so the range of stage here covers down to the section control, we have both these controls affecting it. So we have a control transition. So this is where, at this point, as the water comes up, the river's in section control, and then it changes to a channel control, which takes over from it. And then our shape of our rating and log looks like this. So it goes flatter in section control, and then as we get up the steeper channel banks, it steepens up our curve. So this is also known as a break point in Aquarius. We have to have a break point to tell it we're going to change from this slope to this slope. You'll see this more later. And this is how it will look in a real river. So here's our break point, or our transition between controls. So the bottom section control is moving around, creating all these different ratings. So, and this is then going through this point where they all come together. So this doesn't change much because it's the channel control, but the bottom being braided rivers moving around all the time. That's what it looks like in linear. And this is the actual site here. So you can see how the section control is changing here as this moves with the floods. So this is all the section control. You've got your channel controls at the side and possibly some overbank control here as well. But these are the two main controls for this river. And this moves around a lot at the bottom, as you can see back here. It's moving around a lot. And then we have a third, which we've got section, channel, and overbank control. So all three segments operating. So the range of stage covers all three of them. So you'll have, in this case, two transitions between the three, or two breakpoints. And looks like this in log with the three changes to a steeper channel going out flat again as it goes over bank. And here's an example of that in the real world. So two breakpoints here in Aquarius showing the different overbank flat and steeper here through the channel and then back to the section. And this is the site in reality. The section control here is drowned out, we can't see it, but here's the channel control and then the overbank over the side. Okay, so here you can see the relationship between the control properties and the rating shape. So here's our simple channel control here, where in arithmetic scale it's just a simple curve bend, and in log you've got the straight line slope. And then our more typical river, which has the section and channel control, you'll see in arithmetic it's got the same bend, but it's a bit tighter, a bit more sensitive at the lower end due to this section control, and then it's flattening out. And we have a two straight lines in log with the break point here. And then when we go to the full three, three controls, you'll see the same bottom in it, but sensitivity is good here, and then it flattens out as it goes over the floodplain, and it looks like this in log with the three slopes. So the development of the rating curve, the basics. So discharge measurements are made over a range of flows experienced at the site, and there's always a gauge height assigned to those. So whether you're wading like this or this at the deeper flows, and then heading to boats, cableways, or slack lines for the larger rivers. And it would look like this as the rating curve as you develop it too. So we have pairs of discharges here associated with, here's the flow with the stage. And this is what it would look like at the lower end as we wade the rivers through to boats at the higher flows, and then when it's really high flood flows, we may use slope area or other methods to calculate. So the gauge height discharge pairs look like this. This will just be a channel control, so it's a simple curve here, example. And then as we define it more with the breakpoints between our controls like this, and with measurements above and below if possible. And then as we develop these curves, if it's getting complicated with overbank as well, you'll have these three transitions between the controls, and we tend to try and smooth these out, so you need more rating points around these zones. Otherwise, they're straight curves between. And this is how it looks, of course, graphically, as we saw before. So you've got your section control, going your steeper channel back to overbank afterwards. So these are the control transitions, which you can see here as breakpoints. So here's an example of a real site here. It has one breakpoint. So the log plotting here to offset 1. There's 2 offsets, of course, at this site, one above and one below the breakpoint. And this lower one's represented by a breakpoint at this level here, 1.83. The lower segment has an exponent. So we're talking about exponents now here. You can see it at the back of the equation here of 2.3, which is the slope. And the upper segment goes to a 1.8, which is characterized by just the hydraulics of the channel at the site. And here is a cross section here showing where the section control here, this lower section, to about this point changes to a channel control here. And that's reflected if I go back in here at the breakpoint here. So this point here, which is our 1.831, yeah, this point through here. Yep, there it is there. And that's what the river looks like in reality, looking downstream from the site. And you can see here there's a section control through here to the channel control. And that's a photo of it in flood. Okay, this is more advanced hydraulics and how it concerns our ratings. So the use of the elevation data in our rating development. In other words, this is our surveyed cross-section most places, most times. So this helps determine our gauge for zero flow, which we've talked about, or point of zero flow. We can find that as we survey across the section. It provides a visual plot of the channel shape, which is really handy, and it helps us just relate that to our rating curve shape. It provides potential gauging height range for transition zones, so where our breakpoints will be between the section and channel control and then overbank control. It provides these bank elevations to define the transition zones, all the way up between those control types. Right, and then over the top elevation as well, and how far that might go out. So it would look like this for our Dobson site. So you can see our section controls up as far as the red line, and then it's changing to a channel control. No overbank flow in this case. There's only the one breakpoint or two controls. So some of the fundamental assumptions of the stage discharge rating curve, it assumes a unique relationship between the stage and discharge. That is, for each individual value of stage relates to only one individual value of discharge. So no variable backwater. When we have a variable backwater, so the stage is changing for different flow types. That means we have multiple stage values for the same discharge. So that will not work with this method. It seems a monotonic relationship. In other words, as one variable stage increases, so does the other variable flow, always in that relationship. This is known as simple stage discharge rating. Stage is the only predictor or is a surrogate for the discharge. So as discharge can't be measured directly, well, not yet anyway. So the critical elevation data, the cross-section for a stream with section control, only if this exists. So it should be surveyed to the recorded datum. The cross-section should be surveyed at the section control, so right over the top of it, so therefore we can get that point of zero flow, and up and exceeding the main channel banks. It should be tamed about once every 5 years. It's a NEM standard. It's good to do it maybe when you're running your normal levels for biennial inspection, or following a major control altering events, such as a flood that's known to change the control. Plot of the cross section determining the gauge height of zero flow, and attach this to the field visit in Aquarius, and that can be shown as graphically as well in Aquarius, which is quite handy. If the site does not experience section control, in other words, it's just got a channel and overbank control, the surveyed section should be at the recorder. So not because there's no section control, no control as such defined, you can just do it right where the recorder is. There we are, and it should always be to record a datum as before, and it should include the main channels and flood banks to get all those elevations. It really needs only done once unless there's a major change which alters those banks, which is fairly unusual unless it's a major event. And the plot of the cross section determines that zero flow again and any break points between those upper control changes, and again attached to our field visit in Aquarius. So just a few of the other hydraulic things to consider when we're developing our ratings is the exponent values. So here's an example for a rectangular and a 90-degree V-notch wear. So you can see in the picture on the left, it's pretty crude, but there's a rectangular wear there, and if you look below in the table, you can see for anything rectangular, the exponent values in our equation, which you'll see soon, should always be between 1.5 to 1.8. And when it goes to triangular, like this one here, we're expecting 2.5 to 3, and parabolic, which is somewhere in between 1.7 to 2.8, as a rough guide of what that exponent should be. So here it looks what it looks like in the rating table from the tool itself. So you can see the exponents in this range here at the bottom are showing up as, well, here's the exponents here on the equation. So here's the rating equation here. The exponents are at the end here, and all they are is just our slope, which is the slope of the line. And you can see that for, I think, for this site here, before the breakpoint, we're down in the 1.8 slope range, so it looks like it's parabolic, which is fairly normal for the bottom section control. And when it goes above the breakpoint, it's getting into a higher slope here of around 2.2. So it's almost at the top of parabolic, and then almost going to triangular maybe at that top end. So it's going into this sort of zone, which sort of it makes sense. If you know your river, it's another good check of your rating after you've developed your curve. The offset, of course, in this case, it's the same above and below the breakpoint, but often it's different above. But this offset, of course, is included in here in the equation. And the other part of the equation, of course, is the coefficient, which we don't have any control over, but it's made up of the slope, roughness, the river size, channel shape, gravity, and water density. So that's the three parts of the equation which you'll see in the rating toolbox. So yeah, the rating equation itself, the parameters that we've just been talking about are based on change in the controlling hydraulic factor. So for instance, the coefficient we just looked at is altered or changes with the different slope and roughness, whereas offset's only about bed elevation. As that changes, it changes our offset. And then the exponent itself is all about the channel shape. So you can look at this to give examples, for instance, for the offset. An increase in bed elevation increases the offset. And if you get a flood, it erodes the bed down, you'll get a decrease in the offset. So this is examples here of those parameters in our equation and how it's affected by the river and changes in the river. Let's have a little bit more at look a bit more at the rating exponent. So here's our Great Dobson example again with our cross section. And here it is looking at it, it's a straight line and log here above this breakpoint here at 1.83, yes, same one. And this is the equation here which comes out, and from after generating the curve we get these equations, and we can check the slope here. So we're saying before the breakpoint, before this, the lower end, we've got a 2.3. So 2.3 is in the range, just in the parabolic range really, so it's at the top of that range, which would be because you look like you've got a parabolic curve at the bottom here. And then the top end's going to about around 1.8. So it's either it's in the top of the rectangular really, so it's, you can see it's going more of a straight up and down. If it was triangular, going out on more of an angle, you'd expect these higher exponents. So it sort of makes sense when you look at the cross section. The slopes do agree, so we're just considering all this as part of our rating construction. Let's move on a bit to velocity distribution, the channel shape. So if you have a triangular channel like this, the velocity is obviously, the fastest part of the velocity is under the surface and is drawn back at the surface. So there is a drawback through the surface tension here. Same with a trapezoid channel here, you have the same bend back in the velocity profile, and a narrow one as well like this, and also in a pipe. But as soon as you go to a shallow ditch or a normal river like you would expect, we usually have the velocity faster in the top middle of the river as it flows through. So you have these two velocity profiles. And you've probably seen this if in your results, QRev and Wind River. So this is a typical pow here on the right. And you can see this is a stylized diagram of the velocity profile and how we've always measured it at 0.6, which is the average velocity or the equivalent velocity in the profile, or 0.4 up from the bed. So that's a typical pow and constant no slip example there. And just when you have got a complicated ratings with compound two breakpoints and three different controls, you wouldn't normally have such a harsh control. Normally in reality it would be a smoother one. So we really need to input extra values to take away this abrupt changes in slope. And this can be done by just inserting values each side of the breakpoint table, and that would end up with pairs each side like this, which would help smooth it out. And then you can check this in the rating table and also go and look at it in the rating development toolbox itself. So it should go from harsh like this to more rounded. So it should look like that, which is a bit more what reality would be like. You probably wouldn't need as many points, but you get the idea. It's just smoothing the rating. Yeah, a couple of different types of classic ratings that we tend to see. There's the type curves on the left and the family curves on the right. This is plotted in arithmetic space. So for a type curves are just follow each other up and down. They don't merge. They might get a little bit closer, but they never merge. And so when editing this, we aim to keep the coefficient and exponent, the slope values, the same. The only change is the offset. So the offset is changing as it scales down or builds up. So only the offset is changing with type curves. When it's a family of curves, we approach the aim is to retain the same coefficient and exponent values in the mid to high. So the mid to high is staying the same segment, but we're adjusting the lower end. So we're adjusting the offset at the lower end only. So these would typically need a breakpoint in there to separate those two. Here's an example of the Haast River at Roaring Billy. So in this case here, you can see there's the last three ratings being plotted here at the moment. So all this has been changed by just tweaking this offset each time. So I mean, the easiest way is to clone the rating, the current rating, when there's a new rating happened, and then play around with the offset to suit the following gaugings of this. So it's degrading down. So it's relatively easy to get a combination of cloning, offset changes, checking your slopes. Yes, they're all reasonable as well.